All right, so this is section 4.5 of Math 146. We're going to be talking, as it says, about trig equations. Specifically, we're going to figure out, first of all, how to verify a trig equation, and most importantly, solve trig equations, and come up with all potential solutions on a given domain, or if there is no specific domain, then all potential solutions that you could possibly have. So let's go ahead and get into it. Let's try to verify or determine, let's say determine, if theta is a solution. So we might be given the equation 2 sine of theta minus 1 equals 0. And the theta values that we might be given are theta equals pi fourths and theta equals pi 6. And we're trying to determine if one or neither or both are solutions to this equation. So in order to verify that, just like you would if it was any other variable, you simply plug in the value and evaluate. So for pi fourths, I would have 2 sine of pi fourths minus 1 equals 0. And sine of pi fourths, and we kind of have to know these values, is going to be square root of 2 over 2. Simplifying, 2 times square root of 2 over 2 is just the square root of 2. Square root of 2 minus 1 is definitely not 0. The square root of 2 and 1 are not the same value, so this is not a solution. Let's try it for pi 6. 2 sine of pi 6 minus 1 equals 0. The sine of pi 6 is 1/2. 2 times 1/2 is 1. And 1 minus 1 is indeed 0. So pi 6 is a solution to this equation. And because of the way the sine function is cyclical and the unit circle, every rotation around the circle, forwards or backwards, from pi 6, so all of the coterminal angles to pi 6 would also be solutions. For example, if you were to add 2 pi to pi 6, 2 pi in terms of 6 would be 12 pi over 6. So you would add pi 6 plus 12 pi over 6, and you would get 13 pi over 6. That is also a solution. Add or subtract 12 pi 6 to that, and you're going to keep coming up with more and more solutions. So technically, there are an infinite number of solutions to this, but the ones that they specifically asked for here, out of those two, pi 6 is one, pi fourths is not. All right, so that's if you just have to determine whether theta is a solution or check to see. That's not going to happen an awful lot, although that's good for the end of a problem to see whether you actually have a solution based upon what you solve for. It's good idea always to go back and check. In our second example, we're literally going to now solve. So we're going to start off with one that is relatively straightforward. Cosine of theta equals 1/2. So if I want cosine of theta equal to 1/2, this is not the same as inverse, because that would restrict us to one specific domain between 0 and pi. We are looking for all possible theta values that make this true. It's the same general idea as thinking backwards as the inverse, though. You're looking for the angle that makes cosine equal to 1/2. And if you think about what it would be during one full circle, there's going to be two places that this is going to happen, because cosine is going to be positive in the first and the fourth quadrant. So you kind of have to know what the value is in the first quadrant, and cosine is going to be 1/2 when theta equals pi thirds. So theta equals pi thirds is one solution. But then you also have to go around to the fourth quadrant, which would also be the pi thirds equivalency in the fourth quadrant, which is 5 pi thirds. But as I mentioned before, we want all possible solutions, and all possible solutions here are going to basically be every possible revolution around the circle that could give you pi thirds. So if you add another 2 pi to pi thirds, you would end up with 7 pi thirds. If you add another 2 pi to that, you'd end up with 13 pi thirds. So the concept here is that basically you want to add 2 pi times some kind of a constant multiplier, so we call that k, and we basically say that k is an integer. So for any integer value of k, now this is going to be true. And this is going to hold true for the one on the bottom as well. You would have to add 2 pi k. Again, k would be an integer. So again, all that's saying is for every revolution around the circle, forwards or backwards from that particular spot, all of the coterminal angles are going to be a solution to that equation. So that's a way to do it where there's no restriction on your domain. You have to add 2 pi k. And if you think about it, this should make sense because the normal cycle for cosine and sine is 2 pi. It takes 2 pi to go through one full cycle. So you're going to add 2 pi times some kind of a constant multiplier, an integer in this case, to get to all the next values. Sine would be the same way if we have to do that. But sometimes these will be restricted. For example, let's solve 2 sine of theta plus the square root of 3 is equal to 0, but we only want this to be on the domain from 0, oops, I don't want the equal sign, to 2 pi, to 2 pi. So basically we're saying where does this occur, but only within the standard 1 unit circle. So this one's a little bit easier because we're just trying to find those values. So in order to solve one of these equations, and we didn't really have to do anything with it on the previous example, you basically need to isolate the part of the term that has the theta in it. So you're isolating the trig function that has theta in it that we're solving for. So we want to subtract the square root of 3 and then divide by 2. And now you're to the point where you can say, okay, the square root of 3 over 2 is something which is a standard coordinate point, well, not coordinate point, but part of the coordinate on the unit circle. So now I have to ask myself, where is the sign going to give me square root of 3 over 2? And in this case, it's going to be negative, so it's going to be in the second and third quadrants that are going to give us those values. So again, you have to know, first of all, the square root of 3 over 2 in the first quadrant for sine is going to exist at the pi thirds. But we want this to be in the second and third quadrant because it's negative. So that's going to be 2 pi thirds. There's your second quadrant. And 4 pi thirds is the third quadrant. And again, we are restricted here to 0 to 2 pi. So that's it. Those are the only two places between 0 and 2 pi that this is going to be the case. And I hope somebody has already caught what I was saying to be incorrect, because I don't even know what I was thinking. I was thinking cosine, but I'm talking about sine. Sine is positive in the first and the second quadrants. It's really the third and the fourth where sine is negative. So I completely misspoke that whole time when I was talking about this. So we really were looking for, it's still one of the pi thirds, but we're looking for the third and the fourth quadrant, not the second and third. So I got to erase this because it's not at 2 pi thirds. Sine is still positive there. 4 pi thirds is one of our solutions, but it also has to be 5 pi thirds. So it's third and fourth quadrant. That's where sine is negative. Again, hopefully somebody picked it up and thinking, what is he talking about? And hopefully you already caught that. But unfortunately, it just didn't go very much further before I caught my mistake. All right, let's do something that's a little bit different, because I think those are relatively basic. Let's do an example where we have the sine of a double angle, 2 theta, is going to equal 1/2. And we want this to be, again, on the interval from 0 to 2 pi. Notice we're not including the 2 pi, by the way, because that would be exactly the same place as the 0 if you go all the way back around the circle. So we don't need to include it twice. All right. So this is the same general idea. However, because I've got a double angle, that's going to affect things in the end. The first question you still need to ask yourself is, regardless of whatever that angle says there, you got to figure out where sine is going to be 1/2. Okay, and that's going to be at your pi/6 values. So I do know that sine is going to be 1/2 at pi/6. And the other place, again, now the sign is positive, it's going to be in the second quadrant, which is at 5 pi/6. Here's the trick. These are the places where sine itself is going to give you those values. However, the angle is not theta that we have right there. The angle is 2 theta. And when I want to solve for theta, I now actually have to divide both sides by 2. So really what we're going to get here is that theta is going to equal pi/12 and 5 pi/12. But the problem is there's actually more of these on the unit circle between 0 and 2 pi, and it's because we started off with a double angle. When this happens, if you are going only between 0 and 2 pi, so one full circle, because you have a double angle, you actually need to extend out 2 more, or basically 1 whole more circle, because you're going to end up dividing everything by 2. So up here, I really should have included more. So if I go all the way back around the circle from pi/6, or add a 2 pi to that, again, that's going to be 13 pi/6, because I would be adding 12 pi/6, and then add 12 pi/6 to 5 pi/6, and that's going to be 17 pi/6. And now when you also divide those by 2, you get 13 pi/12 and 17 pi/12. And all 4 of those values are within one circle. So theta is now bound by one full circle. If you go any further, now it would be outside of the circle, because 17 over 12 is less than 2. So that's going to be less than 2 pi. So when you have a double angle like the one that we had there, you're going to have to go 4 values out, or basically what would cover 2 full circles in this step right here. Just in general, if you had a 3 theta in there, you'd have to go 3 circles. If you had a 4 theta, you'd have to go 4 circles, because then once you divide by those values, you'll end everything in the bottom part will end up being within one full circle. All right. Let's look at another example. Let's use a different function. Let's use tangent in this one. So we want to solve the equation tangent of theta minus pi/2 equals 1. And again, we're going to restrict our domain for theta to be between 0 and 2 pi. Same principle as what we just did in the sine one, except that we got tangent values. So you need to ask yourself, where is tangent going to equal 1? And since it's a positive 1, tangent is going to equal positive 1 at pi/4 and third quadrant, which is 5 pi/4. But remember that this is not theta, that's theta minus pi/2. We just set the angle theta minus pi/2 equal to where tangent equals 1. In order to solve for theta, I would need to add pi/2 to each term. So theta is going to equal pi/4 plus pi/2 and 5 pi/4 plus pi/2. And we need to make sure that these are still within one circle, because if we add pi halves now, maybe this is no longer within 2 pi. So let's see if that's the case. Well, pi fourths plus pi halves in terms of force would be 2 pi fourths, so that's going to be 3 pi fourths. And the same idea over here, pi halves in terms of force is 2 pi fourths. So if I add 5 pi fourths and 2 pi fourths, we end up with 7 pi fourths, which is still within 0 to 2 pi. So if that value on the inside of the parentheses of tangent had been, I don't know, pi, so theta minus pi, well, now that second value would have been gone because that would have been outside of our domain. It's not in this case, but it would have been. So you have to double check to make sure that your answers are still within the domain 0 to 2 pi that they gave us. All right. We're going to do a calculator problem, but we're going to do that last. We'll come back to that. I want to show you something that's a little bit more involved because it's going to look very similar to a quadratic. So this will be something which is what's called quadratic in form, and we've done those kind of things before. We're just now doing them with trig. So if I have which is something like 2 sine squared theta minus 3 sine theta plus 1 equals 0. The idea here is that we're going to basically treat sine of theta like it's an x. So if you did this, that would be like 2x squared minus 3x plus 1 equals 0. You would solve that just like a quadratic. So the first thing you should probably think to try and do is factor. If factoring doesn't work, then you might go quadratic formula, whatever you have to do from there. So in our case, if this is going to factor, well, the 2 sine theta has to be broken down, 2 sine squared theta has to be broken down to 2 sine theta and sine theta. Unfortunately, the constant term is 1, so the only way you're getting that is a 1 and a 1. And since that middle term is negative, both of these are going to have to be negative so that when I multiply the ones together, I get positive 1. And when I add these terms together from distributing, you're going to end up with a negative 1 sine and a negative 2 sine, which will add up to negative 3 sine of theta. So now that we've factored this, we're basically going to use the zero product property and set each piece equal to 0 and solve. And I didn't mention it here, but we are going to, I'm going to erase this over here. We are going to restrict this domain once again to 0 to 2 pi. All right, so let's go ahead and solve. So on the first one here, we'll add 1 to both sides, and then we're going to divide by 2. So we have the sine of theta has to equal 1/2. And on the right side equation, we're just going to add 1 to both sides, so we have that sine of theta equals 1. So now we solve each one of them individually. Well, again, on one full unit circle, sine of theta is going to equal 1/2 when theta is the pi sixth, and it will be the first quadrant and second quadrant equivalency of pi 6, where sine is positive. And then where sine equals 1, that's going to be on one of your quadrant angles. As a matter of fact, that one happens at pi halves. And all of those are within one full circle. So those are the 3 values that you would get that would create a true statement or solve the equation from this. Pi 6, pi halves, and 5 pi sixths. All right, let's do 2 more examples, and then I'll show a calculator example, and then we'll be done with this lesson. All right, so if we want to solve 3 cosine of theta plus 3 equals 2 sine squared of theta. Write that a little bit better. This one's a little bit different. Again, we're going to go from 0 to 2 pi. It's different because I've got two different trig functions in the same problem. In order to solve this, you want to try and reduce it down to one trig function if possible. Sometimes that's not possible, but in this case it is, because we can use the trig identities that we should already know. I can't really do anything with cosine. I could make it 1 over secant, but that doesn't really help because that's not the other trig. The sine squared, however, we do have a trig identity. Of the trig identities, this again is probably one of the most important ones. You need to remember that sine squared of theta plus cosine squared of theta equals 1. Well, if I want to change that sine squared into something that just has cosines in it, I want to solve that Pythagorean identity for sine squared, so I would subtract cosine squared from both sides. And now I can substitute 1 minus cosine squared in for sine squared. And now everything will be in terms of cosine. So on the left-hand side, I've got 3 cosine theta plus 3. On the right side, we'll have 2 times, and then it'll be 1 minus cosine squared theta. Now everything in that equation is cosines. So let's distribute the 2. And since this got a squared in it and a non-squared and constants, we're going to treat it like a quadratic at first and see if that works. So let's add 2 cosines squared to the left. And we want to get the right side equal to 0, so we'll also subtract 2 on both sides. So nothing happens to the 3 cosine theta yet. But when I subtract 2 on both sides, we should get, a plus 1 equals 0. So now we're going to treat this just like the problem above. We're going to try and factor it. And this is almost identical, actually, except that it's cosines and there's a sign difference in here as far as the positive and negatives. That has to be a 2 cosine and cosine. Again, that's got to be a 1 and a 1. Everything here is positive. So that one factors nicely like that. Set each one of these pieces equal to 0 and solve each piece. So on the first one, I'm going to do 2 steps at once here. We would subtract 1 from both sides and then divide by 2. So we're going to get cosine of theta equals negative 1/2. And on the one on the right, it's just cosine of theta equals negative 1, subtracting 1 on both sides. So again, from 0 to 2 pi, we have to ask ourselves, where is cosine going to give me halves? And then what quadrants are they going to be in based upon the signs? So cosine gives you 1/2 at the pi thirds, but we want it to be negative, so it should be second and third quadrant. So it's going to be 2 pi thirds and 4 pi thirds. Okay, that's from that piece. And then where is cosine going to be negative 1? Cosine is negative 1 at theta equals pi. Again, that's one of your quadrant angles. So you have 3 solutions: 2 pi thirds, 4 pi thirds, and pi. All right, let's do one more example, and then we'll do, like I said, calculator work. Let me extend the page on here a little bit here. So let's do cosine squared theta plus sine theta equals 2. And once again, we will restrict our domain so we don't have to write the whole 2n pi thing, 2k pi thing out there. All right. So once again, I'm left with something where I've got one of those is squared, the other one is not. So I'm going to replace the squared one. So cosine squared would be the same as 1 minus sine squared, using that same identity that we had above, plus sine of theta equals 2. All right, so I prefer to keep the squared term positive, so I'm going to add everything to the, or excuse me, move everything to the right of the equation. So we're going to get the 0 over here equals positive sine squared minus sine, and then subtracting 1 on both sides, I get plus 1. All right, so this one's going to be a little bit more challenging in the fact that this doesn't factor. Okay, it's not going to factor easily. Your coefficient is 1 out in front of everything, so it's really not going to factor in this case. So what you would want to do is you would want to check to see whether maybe the quadratic formula works here. So you basically need to take the coefficients. It's just the same as it would be for any other quadratic formula. The coefficient A is 1, B is -1, and C is 1. So let's check to see whether this is even going to work. If you use the discriminant, which is just the square root part, so I don't think I've talked about this before, but negative b plus or minus the square root of b squared minus 4ac all over 2a. This right here is what is called the discriminant. If that's a negative value underneath the square root, then you know you can't take a square root of a negative value in the real number system, so we would have no real solutions. If this ends up being a positive value, then we have real solutions, and if it ends up being 0, that's even easier because it simplifies nicely, but that's what we're looking for. So let's just look at the discriminant. So b squared, well, b is -1, so b squared is 1. Okay, we'll just write it out. Minus 4 times a is 1, c is 1. So here we're going to get 1 minus 4 times 1 times 1, which is -3. It's -3 under the square root. We're not going to have any real solutions, so there are no real solutions to this. Okay, if there were, they would probably not be very pretty, but in this case, there are not. All right, so now let's talk about calculator work. All right, let's say that we have something like tangent of theta equals -2. And once again, we're going to do this on one full circle. So the issue here is that -2 is not one of those special unit circle places, okay? If that was square root of 3 or 1 over the square root of 3 or 1 or -1 or something like that, that would be fine. Tangent equaling -2 is not one of those places. So in order to do this, we're going to have to utilize the calculator. And the idea is, because the calculator can't do this the specific way that we want to, there's going to be a little bit of a trick to this at the end. You want to still use the inverse tangent function. The biggest thing you have to remember is the inverse tangent is going to restrict your answers between -pi-halves and pi-halves. So when we take the inverse tangent, and this is the way we'll type it into the calculator, of -2, I believe your book ends up rounding these things to like 2 decimals or something like that. So that's what we'll do for our purposes here. We'll round it to 2 decimals as well. But when you use the calculator to do this, because that value is negative, this is going to place this in the negative first quadrant, basically what would be the fourth quadrant equivalency. But it's going to place it in the negative first quadrant because that's where tangent values would be negative. So let's go ahead and take a look. All right, and the first thing we need to make sure is that the calculator is set up correctly. These are not, this should not be in degrees, it should be in radians. So we got to push the mode button. And my calculator already is in radians, so make sure that that's the case before we do this. So you're going to do the inverse tangent of -2. So second tangent will give you the inverse tangent and -2. And the calculator tells us this is at -1.107 and so on. Rounding to 2 decimal places, that would be -1.11. -1.11. Again, that's something that is currently in the negative first quadrant. So again, this is what it would look like. Wherever that is, down here somewhere, -0.11 radians would be here because that's where the domain is restricted to. but we want this to be between 0 and 2 pi. So there shouldn't be a negative value there from that perspective. So what we're going to do is what we basically need to do is say, okay, if I want to get this between 0 and 2 pi, how do I get this specific place, but by going in that direction? Well, I mean, basically, we already have what it is to here, so why don't we just add 2 pi from here and get all the way back around? So we're going to take our negative 1.11 and add 2 pi. And then see what that gives us. I'll type that in the calculator in a second and we'll write it down. But there's also another place where this is also going to be true. This would also have to be true in the second quadrant. Okay, because the second quadrant is going to basically be the same value, because if you think about it, tangent cycle is pi. So I'm also going to take negative 1.11 and add pi to it. So basically that's going to be something over here. So we add pi, it's going to go to here. If you add 2 pi, it goes all the way around. And these will give us the two places where tangent would equal -2 on the 1 unit circle between 0 and 2 pi. So let's take a look. Pull the calculator back out there. So we would do negative 1.11. Oops. It's supposed to be 0.11. There we go. And we will add 2 pi. So one of the places would be 5.17. Okay, that's that one right there. Kind of a pain to keep getting the calculator out this way. And then we'll do negative 1.11 and add pi. 2.03. 2.03. So using estimations, because those are not exact values since we rounded, those would be the approximate places in between 0 and 2 pi where tangent would equal -2. And for our final example, again, we're going to utilize the calculator here. And technically, we could have done this other one this way as well, and this would have worked. So you could use this to double check that what we just did is also accurate. We're going to have 5 sine of x plus x equals 3. So the first thing you might think is, well, let's subtract 3 to both sides and see if that works. Yeah, that you can do that, but the problem is I've got sine of x and I've got x. So I've got a trig function and I've got a polynomial function mixed in together. There's no way to manipulate those so that there's any difference. So the basic idea is here, what you want to do is plug both of these two things into your calculator in the y equals screen and look at the graph. And again, we're going to round these answers to 2 decimal places. And I didn't write it down, but we're also going to restrict this between 0 and 2 pi. So let's look at the calculator and see how we do this. So we're going to go, I'm going to clear off that screen because I don't need it anymore. We're going to go to the y equals screen, which is the upper left. There we go. And I'm going to input what's on the left side of the equation there, which is 5 sine of x plus x. And then on the next line down, because this is going to be my second equation, I'm just going to put 3 because it's basically y equals 3. And then we want to look at the graph. Now, I personally always start off with a graph of a standard 10 by 10 window. And to get that, if you're not in the right window already, I push the zoom button, which is the middle button on the very top, and then it brings up all the different options for your graphs. I always push 6, zoom 6, standard graph 10 by 10 window. And it should graph what this thing looks like on a standard 10 by 10 window. Now the problem is a 10 by 10 window is going to be definitely past 2 pi. So if you want to restrict it just to 0 to 2 pi, we can do that. We can actually go to our window, which is the button right in between the y equals and the zoom, And we can make our x minimum 0, since we only want to see the x values from 0, and make the x maximum 2 pi, so 2 pi, and notice it'll change that to a decimal approximation. And now graph. Don't push zoom 6 because that'll just go right back. But now you graph with that new window. And what we should find is all the intersection points between 0 and 2 pi. And it looks like there's 3 of them. I'm not going to write these solutions down, but I'm going to show them on the calculator here. So how you find the intersection, well, that's going to be under, if you see the trace button on top, right in blue it's calc, and in green it's F4. So if you want to get to the calculator options, which is going to be a very popular option for calculator work, you would push second and then trace gets you to the calculator. And we're interested in an intersection, so we'll choose selection 5. And what the calculator is asking you, if you see the little cursor there, it's asking you, are we on the first curve that you did? Yes, we are. Don't go up and down because that'll jump off the curve. If you want to move this, you can go left and right. So use the left and right arrows to move the cursor. I want to move this closer to the one on the left to see what that solution is first. So I'm going to move it over here a little bit closer. It doesn't have to be right on, it just has to be close. So then you'll push enter because yes, we're on the first curve. There we go. And now it's asking you, are we on the second curve? Again, use the left and right, not the up and down. Say, yes, we are on the second curve. And those cursors are pretty close to each other. So now it's asking you, can I guess? And yes, you want to push enter for guess, and it should tell you what the intersection is. So y is going to equal 3 at that specific value. And that value of x would be 0.519, or if you round it to 2 decimals, 0.52. Again, just depends on what you're asked to do. So 0.52, and again, that's a radian, 0.52 radians. Then you would do the same thing, second trace, intersection, move the cursor closer to the other intersection. Sorry, it's going to take a little bit longer to get there. Normally, you can just hold the right button down, it'll get closer. Can't really do that on my computer one here. Now I'm on the second curve, push enter. Now I want it to guess, and the second solution is 3.17 or 3.18 if you round it. And then you would have to do it one more time. Second trace, 5 is the intersect. Let's scroll the cursor closer to the other one. And our final solution, enter there, second curve, yes, enter for guess, is 5.7. And there you would have 3 different solutions. Again, I'm not going to write them all down, but that's how you would find them. All right, the video was definitely a little bit longer in this case, almost 40 minutes, but this one's worth it to be able to go through some of the solving of the equations. In our next video for the next section, we are actually going to cover trig identities. So more than just your Pythagorean identities that we know. We're going to cover some other ones.